All right, well, thank you, Steve, and good afternoon, everybody. My name is Josh Goldstein. I head up marketing and product management for XtremIO, which is EMC's all-flash array. And what I'm going to talk to you guys about this afternoon is a few things. I really want to immerse you in XtremIO's architecture and technology, and we'll talk specifically about a few areas that are very unique and differentiated in our product. So one is the ability to deliver consistent and predictable performance. So people think about all-flash arrays as something that will deliver high levels of performance, and that's absolutely something we can do. But delivering consistent and predictable performance is easily as important as delivering high levels. Another thing we'll talk about is how the array architecture allows us to deliver inline data services. This is one of the hallmarks of the product, is that we're able to do everything that the array does inline in the data path all the time, and that also leads into being able to deliver consistent and predictable performance. And then we'll talk a little bit about some of the things that we can do from the way that we've designed the way the array handles its metadata. So we've done some things that are very unique. They're very specific to the scale-out architecture that we have in the XtremIO array, and we can do some very cool things. In fact, there's some great examples of this happening at VMworld Live at the show that I'll describe for you. And then finally, kind of how all this stuff ties together into changing the way that people deploy applications and improving the agility they have in running those applications. So things like their virtual server environments or their databases, we can really make things happen in new and unique ways. I will only spend a minute boasting a little bit about what we've done with XtremIO. The product came to market in the middle of Q4 last year, and in a very short time we crossed 100 million in sales. Took us less than 6 months. We've continued to accelerate from there, and we hit in our second full quarter of availability a greater than $300 million annualized run rate. So the product has been accepted by the market very quickly and is growing very fast. In fact, so fast that, as far as we can tell from all data points, and we vetted this with a lot of analysts, this is not just the fastest growing all-flash array, but the fastest growing storage array that has ever been. So it's really quite tremendous what's happened in a short period of time. So let me introduce you to kind of what we were trying to do with XtremIO by giving you a little bit of an analogy. So when you look at a Tesla Model S, I'm sure everybody's familiar with them by now. And if I asked you what's the #1 benefit that you would get if you bought a Tesla Model S, what's the first thing that comes to mind?
It's electric.
Yes, it's electric. So the thing you would say is, you know, it doesn't need any gas, and that's kind of the whole idea of buying an electric car. But the interesting thing is, if you've ever driven a Tesla, it's really a very transformational experience, because not just is it electric and very efficient in how it uses its energy, but it has fewer moving parts, so it's very reliable. It's really fast, and it's not just fast the way you know from normal cars, but it's very torquey because it's an all-electric design. So you have a very different feel when you drive the car. It's completely silent, which is something that's kind of eerie when you first get in it. It just doesn't make any noise. It's also got more interior space because they don't have to package things the way they do in a normal gasoline-driven car. And the kind of list goes on and on. There's all kinds of benefits of having this car beyond just the gasoline consumption. So similarly, if I asked you what's the #1 benefit of using an all-flash storage array like XtremIO, what's the first thing that comes to mind there?
Speed and no moving parts. But this is the direction that things are going to go. There's going to be no more spindle arrays within the next 5 years or so.
So correct. So the first thing that would come to mind for people is the speed and the performance. Maybe no moving parts is something that you would think of also. But if that's the only reason that you think about an all-flash array, you're kind of missing a lot of the ancillary benefits that you can get as well. So absolutely, you're going to take your performance in the data center to a new level. But also, if you properly architect an all-flash array, you can make things much easier to configure. You can eliminate a lot of the storage, tuning, and provisioning tasks that have been around forever. Because it's flash and it's solid state, you get the power, space, and cooling benefits of that. And if you do the right kind of techniques in the array, you can actually make these very cost efficient. So people will think about flash as being something that is more expensive and you have to pay a premium to get it, but we can actually do a number of things by leveraging the fact that we have a random access media in the array to mitigate those costs. And best of all are kind of the new capabilities, these things that we'll talk about today that we can do on XtremIO that never were possible before, and how that changes the way people do things in their data centers. So My point is that a clean sheet design allows you to take a big leap forward, and you can do it with an automobile, you can do it with a storage array, but you kind of have to rethink everything and not carry forward any of the legacy architecture with you. At XtremIO, we looked at the problem we were solving a little bit differently. A lot of the people that were in the market ahead of us were trying to just do performance acceleration, and we framed the problem a little bit differently. We looked at the things that were going on in a modern virtual data center and said, how can we simplify it? How can we make it faster and make it more agile for the admins? And how can we help enable applications with the storage array that we're delivering? So that's sort of the premise about what XtremIO was designed to do. Now what I want to do is kind of take you from like the bottom up through the technology in the array, and then we'll finish up with how we're able to actually make this happen inside a data center. So let me begin by telling you kind of physically what constitutes an XtremIO system, so you have a picture of it in your head. XtremIO is a scale-out architecture, meaning that we're built out of building blocks, and you can start small with like what you see on the screen here, and then you can add building blocks to scale your performance and your capacity in lockstep with each other up to very high levels. And so the basic building block of our system is what we call an X-brick. And what's inside of an X-brick are two controllers. So you begin with an HA system. The controllers are just standard 1U x86 servers. And then we have a 25-slot DAE, disk array enclosure, that holds standard form factor 2.5-inch enterprise MLC SSDs. And this is a nice scaling form factor because it gives us a very high amount of performance in a small amount of space. And we can be HA from the very beginning, even with a small system, and then continue to grow from there. Now, what's interesting is what's not in the X-brick. So we don't do any proprietary hardware at XtremIO. No FPGAs, no ASICs, no custom flash modules. The SSDs we use are just standard form factor 2.5-inch drives. And we don't do any kind of custom firmware that we have to load onto the SSDs to make it work well in our array. And this is very important because it allows us to keep our focus on developing the best array software and data services features, and not on constantly trying to keep up on the hardware side. There's a huge community out there of people that are focused on delivering the best hardware. We try to leverage best of breed there.
I'm assuming it's all EMC internals, or do you guys leverage external hardware partners as well to build this?
We do, yeah. So the servers that we're using, just think of them as standard Intel x86 servers. They're Sandy Bridge class today. We get them through EMC's Global Hardware Engineering Group, but there's nothing specific about the design that would mean we had to do it internally.
Okay.
Now, when I was talking about scale out, when we add multiple X-bricks into one of our clusters, we tie them together using an RDMA fabric. And this is very important because we didn't want to just tie the controllers together with enough bandwidth to allow them to communicate. The RDMA semantics are actually a very important piece of how our architecture works. And what it lets us do is network together these controllers so that they form one global pool of memory. So this controller can access not only its own local memory, but it can access the remote memory in any of the other controllers in the cluster as if it were its own. And this is done very fast, extraordinarily low latency, and it lets us build systems that behave as one cohesive unit. So we're not constantly ping-ponging I/O around inside the cluster in order to find the right location. If something is on a port connected to this controller, but it needs to access a piece of information on an SSD over here, it's a direct RDMA transfer between those controllers out of the CPU path.
So what's the scale up look like? Can you add more disk arrays to a brick?
Today, so today we cannot add more disk arrays within a brick. It's something we're looking at for the future. But today you would always add in these fundamental brick scaling units.
And the interconnection is made with InfiniBand.
That's correct. Yeah. So it's QDR InfiniBand is connecting everything together, and it's a completely redundant fabric as well. So we make sure that every controller is networked to two separate switches, and that way we can tolerate even the loss of an entire IB fabric.
What's the actual failure domain for, like failure allowance? Is it just a typical N+1, N+2? Like how do you do the architecture, and can you choose the level of sort of redundancy you have within that array pile?
Yeah, you don't get to choose the level. How much redundancy you have depends on a couple of factors. It's sort of what is the failure? It's always going to be at least N+1.
Right.
In many cases, it could be N+2 or N+3, depending on what's failing. And So for example, if I have a controller failure over here, I could also have a controller failure here and there, and everything's going to be fine if I have enough XBricks in the cluster to allow that to happen. Same thing, like an SSD can be failing here and here and here and there. So it gets more resilient the larger it gets. You always have at least N+1 even with a starter system, just a single brick.
And I guess that with the RDMA and all of the metadata that's stored amongst all the memory, I'm assuming that's obviously written in multiple places at multiple times so that you can withstand a good number of failures across the path?
Correct. So we're going to get to more of how this works as we go through the presentation, but the way we distribute metadata is everything is on a distributed journaling process. So anything that we're changing here is also RDMA journaled to another controller. So if this controller fails, there's copies of it elsewhere in the cluster. Things that we have in memory are also then hardened from those journals down to the SSDs and protected there. So everything is very resilient.
Can you handle double disk failure?
We can handle double disk failures if they're in different bricks today, and we're going to be handling double disk failures even within the same brick in a release that's coming up fairly soon. The way our system works, we're already encoding all the data for double disk failures. So in terms of performance overhead, it's already doing everything it needs to encode for double parity. What we're adding in that release I'm talking about is going to be the ability to do a decode of the second failure within a brick.
You use a classic RAID 5 mechanism at this point, or it's something different, RAID 5 or 6? Or?
It's something different. So it's easiest to think about it like RAID 6 because we're doing the double parity encoding. The similarities really end there. I will go into this in more detail, but in a nutshell, we developed an algorithm that we call XDP, or XtremIO Data Protection, and it's flash specific. Kind of the hallmark of the design was we optimized it to be around random access and the ability to place data wherever we want, because we have the ability to locate the data where we want, and optimized for partial stripe updates. And this is particularly important in a flash specific design, because when these arrays come out of the box and the flash is empty, it's very easy to find full stripes to write to. Over time, as you use the array, there's no more full stripes left. There's dirty data in every single stripe. And so if you're always trying to garbage collect out a clean stripe, then your performance profile changes dramatically from the time the array is new till you've used it and worn it in, which I'll show you some data. It happens very quickly, actually. In our system, we maintain that consistent and predictable performance because we optimized for the steady state long-term conditions that every storage array is going to find itself in, which is there's no more full stripes.
Where is the metadata stored? Is that across all the solid states, or what's that look like?
Yeah, the metadata in the array is distributed, and the data is also distributed. Again, we'll talk about this in some detail today, but there's no need. One of the common things that people think about a scale-out design is that the metadata is going to be replicated on every single building block, and then at some point the size of the cluster becomes bound by how much metadata you can store. The way our system distributes things, there's only enough metadata stored on this controller to understand the addressing of the SSDs that are local to the controller, and to have knowledge of where you could find another piece of metadata. So think about it kind of like area codes and telephone numbers. This controller understands the local telephone numbers for its city, but it also knows the area code map for the whole cluster. And if something is being asked for that's in a different area code, it'll RDMA transfer, and this brick over here would have the local telephone number mapped and can get things off of its SSDs.
So what's the total number of bricks in your Lego?
So today we're doing 6 bricks in a cluster, so that's 12 active controllers, and we continue to increase that with every release that goes by.
If you buy 6 today and you release 8 tomorrow, can I upgrade non-disruptively?
You cannot do that right now. So today we sell in fixed cluster sizes, but we also have a release coming, again, not too far away, where you're going to be able to add bricks into existing clusters non-disruptively, and everything will rebalance itself automatically as well.
Everything will be rebalanced. But
Yeah.
the LAN is already balanced in the cluster today?
Yes.
Or, okay.
Yeah, so every LUN is distributed across all controllers and all SSDs in a completely balanced fashion. I'll show you how that works. I promise it's coming up in a couple slides.
So what's the terabytes per brick?
It varies, so you have choices. We can start with a half shelf, which would be 5 terabytes. That can be expanded online and non-disruptively today to 10 terabytes. And then we also have a version with larger SSDs in it that's 20 terabytes per brick.
That's the 800 gig SSDs.
That's right. Yeah. All right, so I think this was actually answer that question too. So, so starting today, we can have a single brick, but half populated with SSDs, going all the way up to 12 active controllers, and this would be 150 SSDs in
So
the
what's the
system.
total usable capacity on the max config?
So on this one, it would be 90 terabytes of physical flash that's usable. And then we'll talk about data reduction techniques, but if you take like a typical 6-to-1, data reduction, that's kind of a mix of various workloads.
1-to-1. I don't trust any deduced numbers because they're never right. But so raw capacity, worst case scenario.
Worst case scenario is 90 terabytes, right? I should say tebibytes because it's base 2. True.
So what about the starter brick? Are there any limitations in using it or upgrading it to the full?
None at all. So actually the exact same performance numbers are what we spec on the starter brick as you do on the full brick.
Okay,
And
no
you-
downsides whenever you upgrade to a full brick.
Say again?
There are
No downsides?
Yeah.
No. It's you get it ends up just being a full brick, and even as a half brick, you still have all the same data services, same performance, everything's the same.
So the only difference is the amount of SSDs.
That's right.
And so performance, everything else, throughput, is it all completely linear from half brick to 12 active?
That's right. Yep. So if you look at our data sheets online, as you go from 1 brick to 2, everything will double. You go from 2 bricks to 4, it'll double again. So this is part of the magic of doing everything with RDMA. It's again, if you were ping-ponging all the requests around the way people had done scale out in the past, then you would end up having a limitation and a very non-linear performance scaling. The more clusters you add, the more inter-node communication there is, and it doesn't really give you any of the gains that you want. We get linear scalability because the data path in XtremIO doesn't change based on the cluster size. It's always a two-step process to find any I/O that we need to handle in the system, whether it's incoming or outgoing.
What is the limitation of the 12 active controllers?
No limitation
No, but why just max 12
instead
incoming?
of a different number.
Yeah.
Because we actually build these and fully test them in QA before we'll release them to the market. So we could come out right now and say we support 48 nodes, but building that and running it through the full set of regressions, having that investment in the lab is something that we've stepped up to over time. And honestly, right now, there's not customers who are coming in and saying, I want a 48-node cluster. This is plenty big for most people's requirements at this point. We know it's going to keep getting bigger, but, but we can stage that.
The process just keep adding to and see where bottlenecks exist.
That's right.
Can you mix different size drives?
So you can't mix different size drives. We want the nodes to be homogeneous, and the reason for that is around system balance and performance. So if you think about, if we have 10 terabyte bricks and 20 terabyte bricks, and if I put those in the same cluster, and I wanted to use the capacity on the 20 terabyte bricks, I have to direct twice as many IOs to them, and now you don't have performance balance anymore. And you start getting back into the mode that people don't like, which is figuring out how to constantly balance things and, oh, this brick's too hot and that one's too cold, I'm not utilizing the resources. So we do homogeneous cluster nodes, and that way everything stays in balance and you always know exactly what you're going to get.